everyone. This is Kruti Jaipancholi, Assistant Professor in LJ Institute of Engineering and Technology in Department of Electronics and Communication. This video is about subject Fiber Optic Communication. So friends, till now we learned about the various source and the detectors used for the fiber optic communication. So now we know that how can we convert the light information into the electrical form, then the electrical signal into the light form. So these are all the conversions that we learn. Now in this video we are going to learn about a few more interesting topics related to the optical fiber communication. We are going to discuss regarding the optical receiver operation. So friends, now we are at the other end of the fiber optic communication block diagram. In this video, we will discuss regarding the receiver performance and the sensitivity and the eye diagrams. So these are the topic for the discussion in this video. So now, let us start with some important and the introductory things related to the optical receiver performance. So now, what is the receiver performance? So in a receiver system, error arises and the disturbance in the signal detection system. What is a noise? So noise is an unwanted electrical signal in the signal processing, and the noise can be the internal or the external to the system, which is defined as the internal noise as well as the external noise. Now only the internal source of the noise that are considered here. So in an optical pulse detection mechanism, various noise exist. Okay, now that can be in the given in the figure. Okay, so now here you can see the block diagram. What is this? The photon system, the energy which can be generated by the particular the light system. So that photon stream that is defined as the HV. Now this the photon detection, quantum noise, the Poisson fluctuations that can be also considered over here. It is given to the photo detector. What is the photo detector? So when the light that falls onto that mechanism, it will convert the light pulses into the electrical pulses. So this photo detector having the gain M. Okay. What is the function of this photo detector? So it bulk the dark current surface leakage current. Okay. Then after the statistical gain fluctuation for the avalanche photodiode. The bias resistor is there, providing some kind of the thermal noise. Okay, and the output that can be connected with the amplifier, and which will also produces some kind of the, if the noise is at the input end, it can be also amplified by the amplifier. So this is the noise sources and the disturbance in the optical fiber detection scheme. So now we need to discuss regarding the noise generated by the spontaneous fluctuations of the current and the voltage. What is that? So the spontaneous fluctuations of the current and the voltage, that can be referred to as the noise, and this noise can be the short noise or the thermal noise. So when the photon incident on the photodetector are random in nature, and the quantum noise that is generated. So this way the noise that can be there in the system. So noise is significant in both the AP-in and the APD receivers. Other sources of the photodetectors, that are the dark current as well as the leakage current. So dark current and the leakage current, short noise, thermal noise, these all are the noise that we need to consider while we are checking for the receiver performance. So this noise that can be reduced by considering choosing the proper components. So the thermal noise which is generated from the detector load resistance. Okay, so detector load resistance that can be there, okay, and due to that the noise that can be generated. So this is regarding the optical receiver performance. Okay, and how can we monitor that? Okay, so that is monitoring by the particular voltage and the current value by finding out the various the noise value. Okay, we can check the performance of the optical receiver. Next is the ISI. ISI, that is the while the digital transmission of the signal that has been done. Okay, so while the one pulse that will be overlapped with the other one, the information can be lost in that particular time, which can be referred to as the inter-symbol interference. So here you can see that, okay, the inter-symbol interference, that is a pulse spreading in the adjacent time slot. So in the adjacent time slot means the nearby time slot, while the pulse that can be spreaded, it can be overlapped with the existing information, and that is nothing but the inter-symbol interference. So that is the inter-symbol interference, and that can be there, okay, in the optical communication in form of the pulse spreading. Okay, so inter-symbol interference also contributes to error which is causing from the pulse spreading. And because of the pulse spreading, energy of a pulse spreads into the nearby time slots, and which is resulting in the interfering signals, and which we have seen in the figure. Okay, so the inter-symbol interference, okay, the energy, okay, which will be there in the appropriate time slot, we have seen it's a gamma. So the total energy in the adjacent time slot, that would be the 1 minus gamma. So that much energy that can be spreaded into the nearby time slot. Okay, so next topic, that is the noise mechanism. So output of the equalizer that can be written as the V out of T is equal to V out of T plus V and T. I mean actual output, that is the output plus some noise. Okay, so that we can write as the V and T, where V and T, that is the noise voltage, and what is a V out T? It's a mean output voltage. Okay, so that is why we can study that the later, that is the noise mechanism, and the noise voltage that can be expressed as the Vn square T is equal to V square short T plus V square RT plus V1 square T, okay, and plus VE square T. So the noise, that is what? It's a combination of all different kind of the noise. Okay, so that is V short of T, that is what? It's a quantum or the short noise. VRT, it's a thermal or the Johnson noise. V1T, which is resulted from the amplifier input noise current source, IAT. And what is a VET? VET, that is requested by the amplifier input voltage noise source, EAT. So this is about the noise mechanisms. So now in the noise mechanisms, the mean square noise voltage that is expressed as Vn square is equal to V square short T plus VR square T plus V1 square T plus VE square T. So furtherly, the thermal noise of the load resistor RB. So this can be written as VR square T is equal to 4 kVT upon RB, BVA R square A square. These are all the equations that we are going to write by the help of the basic equation of the various noise equations, where the kVt is the product of the Boltzmann constant and the temperature. A is the amplifier gain, BBAE is the noise equivalent bandwidth. So this is regarding the thermal noise. Now the thermal noise, due to the amplifier input noise current IAT, So it is V1 square T is equal to S1 B BAE R square into A square, where S1 that is the spectral density of the amplifier input noise current source. Now, the thermal noise due to the amplifier input noise source EAT, that is, so V square ET is equal to SEVE A square. Here the two brackets are given, that is by considering the mean square value of those components. So SE that is the spectral density of the amplifier noise voltage source, and BE that is the noise equivalent bandwidth of the amplifier. So mean square short noise, that is V square short of T is equal to 2Q into I0 N square BBAE R square into A square, where M square that is the mean square avalanche gain and the IA that is the photo current. So the next is the receiver sensitivity. So the receiver sensitivity. So to calculate the optical receiver sensitivity, total noise in the receiver that is calculated. So it is BBAE is equal to I2 upon TB into I2 into B. So where BE is what? So it is the I2B plus 2 pi RC square I3 into B cube. Now substituting these equations, these values and solving the equations, okay. So it is the Vn square is equal to R square A square 2Q into I0 M raised to 2 plus X plus 4 kBT upon RB plus S1 plus SE upon R square I2 into B. So it is equal plus 2 pi RC square, okay, pi square SE I3 B cube, okay, and therefore the Vn square that is equal to the Q RAB square into 2I0 upon Q M raised to 2 plus X TB I2 plus W. So this is the value for the mean square noise current. Now where the W is equal to 1 upon Q square B bracket S1 plus 4 kBT upon RB plus SE upon R square into I2 plus 2 pi C whole square upon Q SE into I3B. Okay, so now this value of the W that we have calculated, so the equation is known as the thermal noise characteristics of an optical receiver. So this is regarding the receiver sensitivity. Okay, now the optimum gain to achieve the desired bit error rate for the receiver, it is given by m raised to 1 plus x optical is equal to 2w 1 raised to 1 half, okay, upon xq into I2. Now assuming no simple interference, the gamma value that is always equal to 1. Okay, so where the q that is the parameter related to the s by n ratio to achieve the desired BER. W is the thermal noise characteristics of the receiver, and X that is the photodiode factor, and the I2 that is the normalized bandwidth. So mean square input noise current, that is the mean square input noise current that is given as IN square is equal to IS square plus IR square plus IE square plus the IT square. Okay, so now these all values we need to find out. So short noise current and thermal noise. What is the short noise? So it is the IS square is equal to 2Q I0 M square A square I2 into B. Thermal noise that is the IR square is equal to 4 kBT upon RB square A square I2 into B. Now the shunt noise and the series noise. Shunt noise is IT square. It is the SI square A square I2B, and short noise that is IE square is equal to SE A square I2B upon R square plus 2 pi c square I3 into B cube. Okay, so now the total noise value is what? It's a summation of all noise currents. So it is the IN square is equal to IS square plus IR square plus IT square plus IE square. Put all the values from the above equation over here, and solving that equations we can have this equation, that is A square in bracket the 2q I0 N square I2b plus q square WB square, and it is S1 plus SE upon R in square BI2 plus 2 pi C square SE BQI3. So this is the value of the mean square noise current. Now we'll solve the next example based on this. The title of the example, that is NINGAAS spin photodiode has the following parameters at the wavelength of 1300 nanometer, where ID is equal to 4 nanoampere, eta is equal to 0.9, RL is equal to 1000 ohm, and the surface leakage current is negligible. The incident optical power is a 300 nanowatt, that is a minus 35 dBm, and the receiver bandwidth is a 20 megahertz. Find the various noise terms of the receiver. So now the solution. Now what are the given data? The given data are the lambda is equal to 1300 nanometer, ID is equal to 4 nanoampere, eta is equal to 0.9, RL is equal to 1000 ohm, P incident, that is a 300 nanowatt, B is equal to 20 megahertz, and mean square quantum noise current. Okay, so now we'll write the equations, and one by one we'll solve the example. Mean square quantum noise current. What is it? So IQ square, that is a Q square root of Q square P incident eta upon HV. So now we'll put the value, okay, of the V in the next equation. So it is Q square P incident and lambda upon C into the H. So now we'll put the one by one value of this, that is the Q square is 1.69 into 1.10 raised to minus 19, okay, whole square into the 300 into 10 raised to minus 9, then eta is 0.9, lambda is 1300 into 10 raised to minus 9 upon H. Okay, the Planck constant, it is 6.626 into 10 raised to minus 34, and what is a C? It is a 3 into 10 raised to 8. So now by putting all the values, okay, taking out the square root, okay, we can have the answer. It is the 2.23 into 10 raised to 11 ampere. Next is the mean spark dark current. Now ID square is equal to 2EBID. Okay, so now put the values of that, all the values in the equations. So it is the 2 into 1.6 into 10 raised to minus 19, 20 into 10 raised to 6, and 4 into 10 raised to minus 9. By solving this equation, we can have the answer. It is 0.256 into 10 raised to minus 19 ampere. Now, mean square thermal noise current. So it is the ID square, it is equal to 4k TB upon RL, where B is the Boltzmann constant and value is the 1.38 into 10 raised to minus 23 joule per Kelvin. So now we need to convert, okay, the degree Celsius into the Kelvin. So it is the T is equal to 25 degree plus 273 degree. So it is equal to 298 Kelvin. So now the IT square, okay, it is equal to 4 into 1.38 into 10 raised to minus 23 into 298 multiplied by 20 into 10 raised to 6 upon 1000. So by solving this, you can have the answer. It is 3.28 into 10 raised to minus 16 ampere. Okay, so this is regarding the example related to the previous all topics of the optical receiver performance, receiver sensitivity. Now the next point we are going to discuss, it is about the eye diagram. What is the eye diagram? So eye diagram, that is a measuring technique for accessing the data handling ability of a digital transmission system. The pattern that looks like the eye, okay. So the eye pattern measurements are made in the time domain and allow the effects of the waveform distortion to observe on the CRO. So now we can obtain that particular pattern onto the CRO. Now here the eye diagram measurement, okay, that procedure that is shown as in form of the block diagram. So the pseudo random generator, okay, the data that can be generated, fine, and which will be transmitted by the optical transmitter and which can be received by the optical receiver. Between the optical transmitter and the optical receiver, the fiber optic cable that is connected. And what is this? This is the system under test. Now the output of this optical receiver which can be connected with the CRO, and the random output which can be also connected with the CRO, and we can observe the pattern. Okay, so that pattern that can be the eye diagram. So to measure the performance of the system, various word patterns that must be provided, various measurements from the eye pattern that can be done. Okay, and that are, okay, the noise margin, timing jitter, rise time, and the non-linearity of the channel. Okay, so now here you can see the eye diagram pattern. Okay, and here in the eye diagram pattern, okay, we can find it out how the distribution, okay, of the particular the signal, what is the maximum particular the signal voltage, okay, what is the minimum voltage, what is the noise margin. Okay, so while the digital transmission, this is the eye diagrams, okay, that can be helpful to us, okay, and we can find out all key parameters using the eye diagram. Okay, so now the display pattern that can be formed when can be understood by considering the 8 combinations of the 3-bit long NRZ pattern, and that can be superimposed simultaneously forming an eye pattern. Okay, so now in the diagram you will see about the 8 particular the possible the 3-bit long NRZ combination of the patterns. So you can see over here, okay, in the first diagram the 1 level and the threshold the 0 level. Again in the second diagram you can see the 0 1 1, then 1 0 0, 1 0 1, then 0 0 0, 0 1 0, 1 1 0 and 1 1 1. So how the various 3-bit data pattern in form of the non-return to 0, okay, how can we get? So this is about the various pattern related to it. So friends, you have studied about the optical receiver performance, receiver sensitivity, ISI and the eye diagram. So thank you very much everyone.